Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, Ricardo Lopes, and today I'm joined by Dr. Chiara Marletto. She is postdoctoral research assistant in the Department of Physics at Oxford University in the UK. Her research interests include quantum theory of computation, foundations of physics, condensed-matter physics, and quantum biology, and those are some of the topics that we're going to cover today. So, Dr. Marletto, thank you a lot for taking the time to come on the show. It's a pleasure to have you on.
Yeah, thank you for having me.
Okay, so, I have to admit that quantum mechanics is not a topic that I frequently address on my channel. It's mostly dedicated to the social sciences and so on. So, in simple terms, what would you say is quantum mechanics about, and perhaps its objects of study?
I think quantum mechanics is this one of the two most accurate descriptions we have of physical reality right now. The other one being general relativity, that is the theory of gravity that Einstein proposed. And the theory was introduced when the previous description we had, which is Newtonian mechanics, classical physics, was found to be inadequate to describe certain phenomenon at the microscale. And the surprising thing is that, in a way, both theories, both general relativity and quantum theory, are really further removed from intuition than Newton's laws. But already Newton's laws were already quite far removed themselves. So in a sense, this is what happens when physics makes progress and so on. But I think in the case of quantum theory, there is a further element of being counterintuitive. And this is to do with the information theoretic structure of the theory. So this is also why the understanding of quantum theory improved greatly with the advent of quantum information, which was something that was proposed in the 80s. And through this new discipline, lots of details about the information theoretic structure of quantum theory were understood further. And I think, therefore, to answer your question about what is quantum theory about, I think it's good to look at quantum information theory, because that's like the essence of quantum theory itself. And the best object that we have to look at in this context is the qubit. So a qubit is like a generalization of a bit. So a bit is a classical unit of information that can hold one or two values, 0 and 1. And the qubit is the quantum version of it. And it's a thing, the elementary entity inside the quantum computer. And it can be instantiated in photons or in electrons or in quantum particles in general. And the main thing about the qubit is that it has a number of different properties, each of which can be measured and observed with maximum precision. But they have this very bizarre property that they can't be observed simultaneously with the same precision. So, if you think of a classical entity like a traffic light, let's say, traffic light can have, let's say, one of two colors, either red or green. And then if you check other properties when the traffic light is red, other properties of the traffic light, for example, is it shaped in a sort of rectangular shape or circular shape, the light inside it. So the property shape is also perfectly definite. So you can observe the traffic light and say, I have a perfectly definite value of shape and of color. And that's because it's a classical object. But if you go to a qubit, or in fact any quantum system, they have these different properties. For example, energy and position. And despite the fact that they can be prepared in a specific value of each of these, so a specific value of energy or a specific value of position, they can't have definite values for both. So when, say, the position is definite, energy isn't, and vice versa. And the qubit is the most elementary entity with this property of having, we say, incompatible observables. And it's very interesting because it looks like you're getting less for to work with like this. In a sense, you have less control on reality, but actually it's not true, because what happens is that when you set the qubit to have a specific value like 0 or 1, and then you let it evolve in the quantum computer through a quantum evolution, then it can explore simultaneously different values of information. And in this way, it can work in a more powerful way than a simple bit. So this fact that it has some complementary or incompatible observables is actually useful for information processing. This is a very counterintuitive fact, but it is what it is. And I think that's why quantum physics is much more rich in a sense than simply classical physics.
Yeah. By the way, when people that are not physicists think about quantum physics, usually we tend to think that it's about probabilities, it's probabilistic. Is that correct? Or at some level, is it also deterministic, like other theories?
That is a very nice question, because so the answer is there is some probabilistic element, but the fundamental elements are not probabilistic, and this is counterintuitive too. So if you just look at the mathematical expression of these of the laws of motion of quantum systems, and the laws of motion are these rules that physicists write down in order to say how objects move in space and time. So if you look at the quantum laws of motion, which are basically either Schrödinger equation or the Heisenberg equations, depending on how you write them, they are deterministic. So they don't have explicitly any stochastic or probabilistic feature in them. There is a completely deterministic flow of the quantum state of a qubit or of a quantum system in space-time. And then the problem is that the probabilistic element comes when one performs a measurement of one of these properties that I mentioned. So when I said that the qubit can have a definite property, but then other properties are not definite, what I meant by that is that if you measure some of these other properties, the best you can say is that you will be able to see one of their values with some probability. And the counterintuitive fact is that this phenomenon that happens at the level of observation, which is stochastic, is then described at the higher level with the Schrödinger equation in a completely deterministic way. And so you can actually include the observer in this deterministic description. And see that when the observer interacts with an object which has one of these quantum properties that are not definite, it interacts with it and gets somewhat absorbed in this indefinite property kind of situation. So the observer itself becomes a quantum object. So there is a completely consistent way of describing everything in a deterministic way, including the observer with the quantum equation of motions. But from the point of view of the single observer, the outcome that are being seen when measurements are performed are actually stochastic or probabilistic. And so these two are two complementary aspects of the theory which coexist. So there's the laws of motion that are deterministic, and then the outcomes of observations are stochastic. And this is sort of expressed by this thing called the Born rule, which is part of quantum theory. And it's a methodological rule that tells us how the pattern of observed outcomes should be within this picture of quantum measurement.
Yeah. Are there any laws in quantum theory?
Yes, so I think the main law is this. It's basically the law of motion of quantum particles, which is I would say the Schrödinger equation, and that is the main thing that quantum theory tells us about the universe, because that law has various properties, And so all of these things I just said about incompatible observables and what happens when you perform a measurement and so on and so forth, they are all somewhat incorporated in this equation. The other law is this. You could call it a rule. It's this Born rule. That is a separate thing from the law of motion, and it's a rule that was put on top of, let's say, the quantum theory mathematical expression by the pioneers of quantum theory, in order to express what probability distribution the outcomes of measurements appear to follow when they are performed. And to this day, I think there is a debate between people at the foundations of physics as to whether the Born rule can be actually derived from more fundamental principles that are non-probabilistic, or whether it's a separate additional law that you have to add on top. And the debate is ongoing, and it's related to the debate about measurement and so on. So these are basically the rules that quantum theory puts on us.
Yeah. By the way, we have the laws of physics, and then we also have information theory. And I read you in your work talking about how information theory rewrites or might rewrite the laws of physics. Could you tell us about that?
Yes. So maybe so one requires a bit of a step back to understand this point a bit better. So I guess. So the laws of physics, as physicists think of them, are really the fundamental rules that say what can or cannot happen in the universe. So there's no escape from that, and somehow there are rules and they exist, and then they, we have some current guesses about what they are, which are the current laws of physics that we are using. We likely will change these laws when we discover a better description of physical reality and so on. But the point is that these laws are not directly referring to information, of course. So information is a different kind of entity, and for decades, actually, it was thought that the whole of information theory was actually a branch of mathematics. So with the work of Turing and people like that, and had little to do with physics. And then I think the major breakthrough came with this quantum information idea, where it was understood by various pioneers. I think David Deutsch is one of them. Then there's Charlie Bennett and others also who kind of grasped ideas such as Feynman, etc. They understood that because computers, which are things that process information, are made of physical systems, different laws of physics, different laws of how physical systems should behave, give rise to different computational abilities in principle. So, if you take a Turing machine embedded in a classical physics setting, so in a discretized version of Newton's laws, you will get certain capability for that computer. But if you then try to do the same with quantum theory, you might get something different. In fact, you do get something different. I think this is why we discovered that this quantum computer has, a much larger set of algorithms that they can run on it, and some of them are much more efficient and so on. So at that point, it was clear then that actually the laws of physics tell us exactly what computations are allowed and what are not allowed. And this is the key link between physics, computation, and information theory. And now, the thing that you might want to do at this point is to say, well, can I push this logic a little bit further, and then say, well, I can see that by using, by adopting this information theoretic approach to quantum theory, I can extract the very foundations of the theory, of this physical theory that is very fundamental, and I can talk about the essential elements of the theory without actually worrying about the details of physical systems, because everything boils down to being either a qubit or a collection of qubits. So you forget about the details of specific physical systems. So, a photon and an electronic spin behave in the same way as far as information theory is concerned, and you can call them both a qubit in certain sense. So by doing this step, you can get at the very foundations of quantum theory. And so the question is, can you actually now use information theory in order to extract the very basics of a physical theory and get some guiding principles that are more general than that specific physical theory, and they can actually constrain further theories that we don't yet know. And I think this is where this work of mine is going, in the sense of what I'm trying to do with some of my collaborators, David and other students as well. We are trying to see whether it's possible to extract some kind of basic symmetry that's present in the current laws of motion that we have, quantum theory, and express it through more general principles that only refer to information theoretic entities. And in this way, we are also hoping to be able to constrain and give guiding principles in order to guess future laws of physics. For example, there's this search for theory that could put together quantum physics and gravity. And some of these guiding principles based on information could constrain this theory too. So that's where we are going, I think.
Mm-hmm. So you are also trying to integrate quantum mechanics with general relativity and trying to arrive at an explanation for gravity from a quantum mechanical perspective. Is that it?
Well, so I think I'm not. So my work is, I'm not working on quantum gravity directly. But what I'm doing is that I'm trying to. So there is this problem. So lots of physicists are working in that area, and I think the hope is that what I'm doing with this information theoretic approach can be helpful to them in order to have constraints that tell them where to look for, let's say, producing this theory, ultimately, the quantum theory of gravity that is fully viable and testable and so on. And why is this important? So I can tell you like a more general point about this principle take on things. For example, in thermodynamics, we have a similar logic where you have very general statements about, say, the fact that perpetual motion machines are impossible, and this is to do with the conservation of energy and also with the second law. And these statements are more general are more powerful, let's say, than any specific law of motion that has been proposed, because we know, say, the conservation of energy was true for Newtonian physics, is still true for quantum theory. Modification of it is true also for other theories we know, and so on. So I think these principles can be very powerful because they don't specifically talk about a law of motion, but they have this overarching power of restraining future theories too. So when a physicist is looking for a new theory, they want to make sure that it satisfies some of these basic principles. Another one is locality, for example, and so on. And I think the information theoretic principles that David and I proposed recently have the same logic, in the sense that they should be also used in that sense to help theorists to find new laws.
Mm-hmm. At a certain point there, you mentioned computers. What is a universal computer? And I mean, I guess that in physics, when you talk about computers, you are talking about machines that can perform tasks. Perhaps you can also explain what a task is in theoretical physics.
Yes, I think the general idea with a task doesn't have to be a computation. It could be a more general task. Is that it's a specification of a transformation. So intuitively, there's an input and there's an output. So for example, when you say I want to cool a can of Coke from a certain temperature to another temperature, that is a task, and the substrate is a can of Coke. And you would, like to do this with a certain amount of energy. That is the thing that you use for the fridge to work and so on. And in the case of computational tasks, computational tasks are special kinds of tasks that involve degrees of freedom that can be used in general for information processing and so on. And a computer is an object that can take in input some physical system initialized in a certain state. I mean, let's say if it's a bit, it could be 0. And then by interacting with it, it can deliver the same system with the desired output state. So, for example, the task could be to send 0 to 1. And the computer that performs that has to have this crucial property of retaining the ability of causing that transformation again. So you want the computer not to explode at the end, but to be reusable as many times as possible. Ideally, it would be nice to be able to use it forever. And so it would be nice for the computer to be able to work in a cycle. So that's in the ideal setting, for example, in Turing machine setting, you're thinking of a computer that interacts with the system in question, changes it, and then comes back to its original set of states. So works in a cycle and it can be reused. So in that sense, a computer is a special case of a constructor, which is this general machine that can take an input, deliver an output, and stay unchanged in its ability of causing that transformation again. Now, with a computer, you can take a very special, you can think of two different tasks. For example, you can think of the one I said, the changing 0 to 1, and the 1 to 0, which is performing a knot on a bit. And then you can think of some other computational task, a more complex one, maybe if you have two inputs, you would like, for example, to add them. So, you're given 0 and 1 bits, and then you want to add them modulo 2, let's say, and get in output the addition. Now, the thing about the universal computer is that a universal computer is a computer that is capable of performing all computations that are physically allowed. So, for example, if, say, 0, 1 goes to 1 and 1 goes to 0 is allowed, is possible, and also the addition is possible, which is a different transformation, that doesn't just mean that there are two different machines or constructors that can perform, two different special computers that can perform NOT and addition separately, but there can be a unique machine, which is this universal computer, that can perform either of those tasks when specified which one to perform. So it's a very special and important property that is allowed by physics. The fact that you can imagine for each computation that is possible, there's always a machine that can perform all of these computations together without resorting to a further machine. So in a way, it's the most powerful computer in terms of repertoire, it's the most general computer that you can imagine existing in this universe. And turns out it can actually perform all the computations that are allowed physically. Yeah. And let's say the one we are using now is an approximation to that computer. And the universal quantum computer is exactly a universal computer which works under the laws of quantum physics. So it includes, in addition to the stuff that this computer can do, all the other new things that you can do with quantum systems that this computer can't perform yet.
Mm-hmm. Yeah, at a certain point you mentioned constructors and you explained what are they. And okay, what I would like to ask you now is, what is constructor theory? I mean, what are the kinds of questions that it tries to answer?
So I think constructor theory was proposed by Deutsch, who also pioneered the quantum computer, as was intended as a generalization of quantum computation to dealing with more general tasks than just computations. And you might wonder why you would like to do that. So, I can explain a bit why one would want to do this generalization. So the quantum computation enterprise is one that has been very successful. We are trying to get into realizing this universal quantum computer and so on. But there are two ways in which the universal quantum computer is not quite the most, the most general machine that one can think of. So on the one hand, there's the fact that quantum theory, as I said earlier, might end up, actually will probably end up being modified in order to incorporate gravity one way or another. And so, because at the moment, as I said, quantum theory and general relativity, which is the best description of gravity that we have, clash. So they don't agree. So in order to have a consistent picture of the universe, we have probably to modify both theory. And then, so you could say, well, supposing I have this new theory, which is no longer quantum theory, will I still be able to have a notion of a universal quantum computer, and what will it look like? So will I still have all of these quantum phenomena that are important for quantum computation, such as quantum effects, such as entanglement, quantum superposition, and so on? And unfortunately, the answer can't be found in quantum information theory, because quantum information theory really assumes the whole of quantum theory. And therefore, it has to be updated to incorporate this, possibly this future theory that we don't have yet, but we will have at some point. So you would like to have a more general take on quantum phenomena inside the quantum computer, to talk about them from the purely information theoretic point of view, avoiding any detail that is rooted just in quantum theory and is not general enough. So that's one way in which you want to generalize quantum information theory. And the other sense is that a universal quantum computer is not the most general machine. So there are some tasks that are not computations, which the quantum computer cannot perform. And this was already been discovered by von Neumann, who is this polymath who pioneered quantum theory, but also other very, very interesting ideas in computer science and so on. So he noticed that a universal computer like the Turing machine can do all sorts of computations, but it cannot perform this very basic task of producing a copy of itself. So if you try to program a computer to perform on itself the same thing that, let's say, a cell can do, which is self-reproducing, the computer won't do it, because it's not equipped to do that. It's not, it's only equipped to work on its computational space, but cannot look at itself and reproduce a copy of itself. That's not one of the functionalities of Turing machines. Whereas a constructor, which is this more general entity that can take in input not just information and things, but more general input substrates, can in principle do that. And so von Neumann pointed out, therefore, that this idea of a universal computer wasn't universal enough, and you should think of a machine that is called the universal constructor, which can perform any tasks that's physically allowed. And from the point of view of technology, of course, this is very, very far in the future. But if we had one, this would completely revolutionize what we can do, because you think of anything that's physically allowed, you would have a software that you just put into this machine and it would do it for you. So, you could construct a house, or, it would be like a generalized 3D printer that can do whatever, so long as you input the right kind of program for performing that task. So in those two senses, I think if you take the theory of computation, you could generalize it to something more general. And the constructor theory idea is to do that. And I think, so David proposed this very general program. And then I joined forces, because I was then a PhD student here in Oxford, and I was interested in some of these ideas, and finally, actually, we ended up collaborating on something, which ended up being this work on information theory. And as we went along, with these problems, we realized that actually there could be more scope to this theory than it originally looked. And the current way in which I'm thinking of constructor theory is that its principles, its laws, can be used in order to do what I said earlier. So they can provide guiding general principles only expressed in terms of possible and impossible tasks that can supplement the dynamical laws, and they can give us a guiding a set of guidelines in order to conjecture future laws of physics. And I think, so in a sense, I think of constructor theory as an ultimate generalization of thermodynamics and of information theory together. And that's actually the direction in which I'm pushing it at the moment with my research. And it's very exciting because it forces you to think of familiar concepts that you know from usual dynamical laws, usual laws of motion, from this different point of view, where the most fundamental statements are about tasks being possible or impossible. And by doing this kind of logical switch, you learn a lot, both about the theories that you already know, but also about what kind of theories you might learn, you might find in the future. And so I think that's the current, the constructor theory is mostly at the moment still a program, so we are in the process of realizing it. But that's the logic behind it, and let's say where we are going at the moment.
Yeah, and could it apply to other areas of science like biology, for example, in trying to understand the origins of life?
Yes, this is so I think the theory is very general. So my current focus is physics, of course, but this intuition that there is a fundamental dichotomy between tasks that are possible, where a constructor is allowed, and this constructor is this entity that can work in a cycle to perform a transformation, and then meaning stays the same in its ability to perform the transformation again. So this intuition that there is a dichotomy between possible tasks for which a constructor is allowed and impossible tasks for which a constructor is not allowed is actually a very general statement. And so in biology, for example, you can find, of course, instances of constructors, approximate constructors in cells and organisms and so on. But I think you can also use this set of tools from constructor theory to talk in more general ways about some aspects that are key to biological evolution, for example, because as we know, biological evolution is all about information being processed and a certain sequence of, say, DNA being selected over others, and the whole information processing of natural selection has an ability which is very interesting, which is to create knowledge out of stuff that doesn't have knowledge. So, for example, you start with a bunch of chemicals that are in a certain environment, and then if you wait for long enough through this blind process of natural selection, you can get organisms that can actually move in that environment, and they also have knowledge about what's going on around them, and they can self-preserve. And these concepts of information that's useful, which I call knowledge, information that has some biologists say that has causal power. So the knowledge in DNA is capable of supporting itself, of self kind of reproducing and surviving across generations, is a concept which has to do with certain counterfactual properties to do with what's possible and impossible. And so the way you can distinguish knowledge, useful information, from mere information that doesn't really have much use is also based on certain possible and impossible tasks. And I think, so constructor theory can give you a very nice, precise and exact definition, objective definition of knowledge, which is different from, say, other notions that are more subjective and observer dependent and so on. And the other way in which it can be useful for biology is this way of exploring the connection between the principles of biology that we currently have, such as this principle of natural selection that says, that most organisms, that all the organisms we have must have come about through natural selection, and the way, the laws of physics that we have. So you could look at the way in which, say, natural selection occurs, and the fact that biological entities are ultimately made with this thing that's called by Dawkins the replicator vehicle logic. So the cells, the way they self-reproduce, usually it's by having inside like a recipe or a string of information that describes the way they are constructed. And the self-reproduction occurs by the cell executing a program in this recipe to construct a new vehicle, which is basically the cell bar, this information bit. And then the information part is then copied bit by bit in this new replica of the cell, and that's how the new cell is born. And this logic, which is kind of viable and exists in nature, you could say, is it just sufficient? So it's just something that happened to be developed like that from scratch, or is it really the only one that's viable given the laws of physics that we have? And with constructor theory, you can make an argument, which is very nice, that if you assume that the laws of physics are elementary in the way that we want as physicists, so we don't want to have any special design for life in the laws of physics, then the only viable logic for having accurate self-reproducers is this one that I just said, so the one that uses the replicator vehicle logic. And it's nice because this kind of tells you that if you go randomly in the universe and you kind of find another form of life, never mind what chemistry is made of and what kind of particular elements it's using in order to sustain itself, you will find somewhere this replicator, the DNA-like entity, which is a recipe for the organism, and the way in which whatever form of life you're looking at self-reproduces will actually be through this replicator vehicle logic. And this is a prediction you can get from, say, the current laws of biology that we know, evolutionary biology, and from these other more general principles about information theory that you can get from constructor theory. And if you put them together, you get this nice prediction. So I think that's how it can be applied. And there are probably many other ways. And in fact, I mean, I've had various discussions with astrobiologists and people who are interested in these kind of issues, the origin of life and so on. So hopefully it will be even more useful than this.
Yeah, it's very interesting. Does this theory, constructor theory, have any implications for how we understand how things like causality works and also free will?
Yes, so I think again this is going into this direction of more speculative and not so directly related to physics kind of ideas, but this is something that interests me too. So the first thing to say is that, I mean, the notion of cause in everyday life is very intuitive. So we can say, I pushed this cup off the table and I broke it, and my thing was the cause of this thing happening. But if you go to the laws of physics and you look at them, you see that, and this is something that lots of physicists have noticed, you see that there is no space for such a notion at the fundamental level. And the reason basically is this, that the laws of motion of particles are reversal, are symmetric in terms of reversing the flow of time. So if you let something evolve in time and then you rewind this motion, both things are actually allowed. And in a way, you could say, well, this molecule hit this one and it made it, say, move from here to there. But you can also say, because the laws can go the other way around in terms of time, that it was this other molecule hitting this one and then making it go that way. So because both trajectories are allowed physically, there is no sense in which you can say that something that comes before another caused it at the microscopic level. So that's why physicists have usually a problem with the idea of cause. They think, oh, it's an arbitrary thing, and it only makes sense at the level of humans, so it's not very fundamental and so on. With constructor theory, I think, and not just with constructor theory, this is more like a more general thing that also is present in thermodynamics and so on. You can define a cause in a different way. You can think of it in a more fundamental way, I think. which goes around this problem, is still compatible with this idea that the laws, the fundamental laws, are time reversal symmetric and so on. But you can think of a constructor as being a cause for a task. Why is that better to think of it like that? Because you see, the constructor, if you let the process unfold, where the constructor performs a transformation and changes, let's say, a bit from 0 to 1, the constructor is the only object in the surroundings of the bit that retains the property of enabling this transformation again. So it's something that can interact with the bit, enable the transformation, so it induces a change on the bit, but while doing that, it stays itself, so it doesn't change, it doesn't modify at least part of its properties. And so this ability of staying unchanged is the thing that singles out a cause from other things that are not causes, but they are just kind of acted upon by this cause. And in that sense, I think there is a more objective ground for talking about causes, which, as I said, doesn't rely on observers or other things like that, which is already a good thing, because then we're not going to subjective entities that physicists don't like much. And as far as free will, I think that's a much more serious problem in a sense. So I think, well, there are currently various arguments that allow you to be a scientist and to be a physicist and be happy with the fact that the laws of physics are deterministic and so on, and at the same time be able to think of your own self as having self-determination and being able to make choices, etc. And these are approaches that go under the name of compatibilism. Dennett and others have sort of advocated these kind of positions. But somehow in these accounts, not all problems are really addressed, I would say. So there is a sense of still there being some kind of issue where ultimately you have to concede that free will is just maybe some emergent thing that's not very fundamental, or maybe it's just a thing that we happen to perceive at our scale but doesn't really exist and so on. Now, so because I think there are still some open problems, I still think that maybe the complete scientific understanding of what free will is and how to integrate it with physics is perhaps, requires still some thinking. Specifically, it requires some thinking in defining what is it, what's the property that we are actually trying to say is compatible with the laws of physics. So when we say free will, people think of different things. They think of as I said, the ability of making a choice that's free, but also they could think of creativity. So, when you suddenly decide to go for a swim, as opposed to, having a stroll on the beach, that's happening because your brain created a new interpretation of the situation that you're in. And somehow suddenly you think it's more fun to go for a swim than having a stroll. And that creation of knowledge is a process that's to do with creativity, with the ability of the brain to create new knowledge. And I think this specific thing hasn't been quite understood yet in terms of, we don't even know how to define it properly. Is it consciousness? Is it something more than consciousness, and etc.? And of course, this is related to the AI research and so on. So I think this is very much an open question. Having said that, I think constructor theory at the moment has nothing to say directly about these things yet. But what it can do is that it provides a way for physicists, I think, and for scientists in general, to think of this knowledge thing that I said, so information that has causal power, or it's useful information and so on, in a more objective way. So because it's, as I said, knowledge is, in constructor theory, is information that can remain instantiated in physical systems. So it's capable of causing itself to stay instantiated in physical systems. So it's resilient information, if you like. And this is, when defined in terms of possible tasks, which you can do in constructor theory, you have a handle on a concept which would otherwise be very, would otherwise be possibly fuzzy or subjective, something that doesn't quite appeal to physicists. You have a handle that is, on the other hand, objective and scientific. So hopefully this is a conceptual set of tools that you can use in order to tackle this question. So I think that's how I see constructor theory coming in as a useful tool, possibly in the future, to address this issue.
Yeah. Another question, is reality, or at least the way we perceive reality, an illusion? Could we say that?
Yes, it depends what we mean by illusion, in the sense that, right, that it's a nice question. So in a way, physics has shown that what we see is not quite what is out there. So just think of the appearance of the sun moving across the sky during the day. That would suggest something, and actually reality is different. The sun is not moving around the Earth, so motion is actually much more sophisticated than just that. And it took ultimately Newton to come up with some laws that explain what's going on, really. And ultimately the reason for what's going on is gravity and so on. However, that doesn't mean that, likewise, just of course with quantum theory, back to quantum theory, we have an appearance of something that's completely classical. We don't see these incompatible observables. We don't see qubits in our reality around us. And yet we know that quantum theory says that they are there, and we are made of qubits too. So, the reality is very different from what we thought it is. But that doesn't mean the reality isn't there. So I think there are some, especially some readings of quantum theory that tend to extrapolate this fact that, for example, observables don't have definite observable values and so on, to say that there's nothing there. And I disagree with those views, and I think, of course, ultimately, as a physicist, you will see that there are different positions around, but the position I favor is the one that says that there is a reality out there, and so I'm a realist in a sense, and that what we're doing with these further laws of physics that we find, as we tentatively make progress, is just to guess better and better how these entities out there are. So we are just making better and better guesses as far as what reality really is, and sometimes when you do that, you discover further problems that hint at further bits of reality being there. And in a sense, I don't see an end to that. So, for example, we now currently think that there are certain elementary particles, but at some point it could be that we might have to revise the idea that those are the most elementary particles we have, because there could be further elementary particles. And likewise, now we think that certain objects like light behave as a field. It's made of objects called photons, and they behave in certain ways that quantum field theory tells us. But that view too could be revised, and we could find more elementary entities that compose photons and light and so on. So I think this is very much, so this picture of reality that we have gets always improved upon. But I think ultimately there is some reality, and what we are trying is just to improve our understanding of it in a tentative way. And that's what physics really is ultimately about, and the whole of science is about.
Yeah, fascinating. So finally, I have here a question from a patron of the channel, Bernardo Seixas, and
yes.
He says, Dr. Marletto, you have published papers on the constructor theory of information and constructor theory of life. What's next for constructor theory?
So I think the two things that are next, which are actually already happened in the last couple of years, is that So one thing is to apply constructor theory to thermodynamics. So what I was saying earlier, that we currently have some laws of thermodynamics, the second law and the first law, and they are about perpetual motion machines not, being allowed in certain ways and so on. And these laws were very useful for, say, explaining things that happened during the first, the Industrial Revolution in the Victorian era and so on. So heat engines that powered trains and machines of that kind. But the laws are somewhat breaking down when you consider very small objects. So, if you, again, go back to an electron or or a single atom or something like that, you have a problem in defining, say, what work and heat are in that context. And reason is that heat and work make sense for these macroscopic machines, but they don't make sense for single microscopic entities. And so some people tend to then say, okay, well, that's not a big deal because, we can just say that heat and work are not very useful. They're just useful at the macroscopic scale, but they're not fundamental. But then there are other people, and I'm kind of side with them, that think that there could be a way of generalizing these laws of thermodynamics to the microscopic domain. And constructor theory has a very promising handle on that. And I think one of my recent works is exactly about that, to define work, thermodynamic work, at the level of a single particle. Instead of thinking of these macroscopic entities, you just consider a single particle. And the reason why what I'm doing is interesting in that domain is that it's trying not just to use the dynamical laws that we know to describe the microscopic particle, because of course we could use those laws and then we would get something that makes sense, kind of is in agreement with quantum theory and so on. But I'm trying to provide a general principle that doesn't, again, rely specifically on quantum theory. So I'm trying to preserve the generality of the second law as we know it for macroscopic objects, and still maintain that at the microscopic scale. So that's one big direction. So it's the constructor theory of thermodynamics, and I think there are some students. Maria Violare specifically, she's working on this with me at the moment, and I think we're making good progress on that direction. There is another direction which is a bit more on the side of these things I said earlier, of using constructor theory's principle to put constraints on systems that don't necessarily obey quantum theory. And of course gravity is the main candidate here. But there could be other systems, such as, macroscopic systems that may collapse away from quantum theory and so on. And in this area, I think there has been very nice development of a recent proposal for testing the presence of quantum features in an object that doesn't necessarily obey quantum theory. And I think this is something that I worked on with Vlatko Vedra, who is another physicist here at Oxford, and I'm also working on with some other students. Niceto Tibalo-Vidal is one of them, and Simone Riavec, I think. And I think we are making good progress in trying to use these principles to tell us how to test, how to probe these objects where the laws of quantum theory don't quite hold exactly, but we can still make some useful predictions that can allow us even to propose some tests. And I think recently there has been a connection with experiment as well. So I think that's also very important that, I just wanted to add in general that I think my prior work was mostly on the theoretical side, and I'm still kind of very much on that side. But I think it's very important to find a connection between these general principles and then some experimental consequence. And I think that's where these two directions I've just mentioned are driving at. And I think this is where we will be in a few years. So that's, let's say, my expectations for the future, if the theory works as we expect.
Yeah, great. So, Dr. Marletto, let's end the interview here. Just before we go, where can people find your work on the internet?
So I think there is constructortheory.org, which is this website where we usually post updates on my work and the work of my team. And I think there you will also find some nice explanatory material if you're interested in kind of reading more about this. And in May next year, I think my book, which is called The Science of Can and Can't, is going to be out. So Penguin is going to publish that, and that's also a place where you can read more at a kind of more popular level about these concepts that I mentioned today. So and hopefully more things will come up. So.
By the way, do you already have a publication date for the book?
I think it's the 4th of May in the US. And I think May probably in the UK as well, but I wouldn't swear on which date, so I have to double check on that. But I think around May, let's say next year.
Okay, so I will leave another invitation on the table to talk about your book next year. Sorry?
Yeah, wonderful. Thank you. That's great.
Yeah. Okay, and thank you again for taking the time to come on the show, and it was a real pleasure to have you on.
Yeah, same here. Thank you so much. I enjoyed it very much. Yeah.
Hello everybody, thank you for watching this interview until the end. I've started this channel back in February 2018 and have been putting out regular interviews with academics and intellectuals from a variety of fields. So to keep the channel sustainable, I would like to ask you to consider making a pledge on Patreon. I have the link in the description box, or on PayPal. You can also find the links there. And otherwise, and if you like what I'm doing, please share it, leave a like, and hit the subscription button. I would also like to give a huge thank you to my main patrons and supporters on PayPal: Karen Litzke and Blanchett, Paroga Larsen, Lau Guerrero, Francis Ford, Hans Fredrik Sunde, Ricardo Vladimiro, Craig Healy, Adam Kessel, Olaf Alex, Jonathan Wiesel, David Diaz, Anian Kata, Jacob Klinkby, Matthew Whittingbird, Arno Wolf, Tim Hollacy, Enric Alenius, John Connors, Paulina Barron, Philip Force Connolly, Jerry Mueller, Herbert Gintis, Rutger Voss, Bo Weingart, Rebecca Newberger Goldstein, Dan Demetriou, Robert Rui Inácio, Arthur Coe, Zup, Marco Neves, Max Bailby, Colin Holbrook, Susan Pinker, Thomas Trumbull, Bernardo Seixas, Pablo Santurbano, Simon Columbus, Jorge Spinha, Phil Kavanagh, Corey Clark, Mark Blythe, Roberto Inguanzo, Michael Stormer, Eric Neumann, Samuel Andreev, Tiago Nunes, Bernard Hughney, Alexander Dunbauer, Omari Hickson, Felicia Stevens, Fergal Cusson, Yevon Bodrenko, Al Herzog, Nuno Machado, Don Ross, João Alves da Silva, Jonathan Librant, Oslam Bullet, Nathan Nguyen, Staten T, Samuel Correa, Eric Hines, Mark Smith, J.W., João Eira, Tom Hummel, David Sloan Wilson, Yacila Deza Araújo, Ethan Solon, Romain Roch, Dmitry Grigoriev, and Diego Londoño Correa. My producers, Isar Webe, Jim Frank, Lucas Stafiniak, Ian Gilligan, Sergio Quadriano, Luis Caetano, Matthew Lavender, Tom Van Egdam, Curtis Dixon, João Linhares, Benedict Mueller, Vega Guidi, Sardas France, and Niruban Balachandran. And my executive producers, Michal Rojewski, Rosie, and James Pratt. Thank you for all.